Welcome to Unit 2, Part 2, Error. As it goes, to err is human. Error is imperfection. It's inevitable. We're not perfect. Anything we do will be imperfect inherently. Now, a couple quick points though. Error isn't certain things we like to call error. At least in the statistical scientific term, error is not a mistake. Mistakes are things you go redo it because you messed it up. You did it wrong. Error is not misinformation. It's not lying. Lying, that just means you're a jerk. Don't lie. Error is the imperfection in the measurement. It's when everything went right, you still don't have a perfect measurement. And so we're going to need to deal with error. And to do that, we first need to start thinking about where it comes from. And there's really two types of error in our measurement. First is random error, and this is kind of where we're hoping our error is coming from. It's just noise, it's random events. If you take multiple measurements of the same thing, presumably they would be exactly the same, but in reality, they're probably not. There's a little bit of variation. Hopefully it's a little bit, not a lot. Sometimes you get unlucky. But that variation is kind of all over the board. There's no real clear cause to what's going on. That's known as random error. Now, when we think about this, this is going to cause a drop in precision. Precision is how close your measurements are together. So I've got the bullseye up here. If I'm precise, my measurements are close to each other. Accuracy is the counterpoint to that. That means how close I am to the true value. Now, presumably it's hard for me to know what the actual true value is, so precision is a lot easier to tell. Systematic error is really error in the accuracy in many respects. That means all of my measurements are off by a little bit. And so in this case, I've got the inaccurate but precise measurement. The average of those spots is not on the bullseye, but they're nice and close together. Now, you can do a measurement where you do know the true value, and we will do this quite often. Where we will run experiments where we know the true value, and then we'll run the same experiments where we don't. And that way, if I can get the correct answer the first few times, then presumably when I don't know what the correct answer is, because I'm running the experiment. Why else would I be doing the experiment if I didn't know what the correct answer was? Then I can trust my results. I used to work in a lab where we analyzed samples of heparin for quality control, and they wouldn't tell me which ones are which, but they give me about 27 samples. Only one or two they actually cared about. The other 25 samples were one that they knew what was in it, and they were testing me. If I could get the 25 right, then they could trust me on the two, and people's lives were literally at stake if I screwed that up. So, 25 checks for two good samples, possibly even just one. The good samples are known as standards. They're things that we know what they are. So those, once again, can be a chemical. For me, that they were a white powder that contained heparin or a couple other different chemicals. Alternatively, they could be some kind of device, like the aforementioned platinum iridium orb in France, if you're looking for a standard prototype kilogram. There's something in which you are going to compare your instrument, the device that's measuring stuff, to a known true value, and those are going to be the known true value. If you get it right, then you probably don't have systematic error. If you do have systematic error, you're going to be able to see it. If you have standards, that's probably an issue with your instrument. Sometimes, if you understand what's going on, you can mathematically correct for it. Other times, you can't. So when we deal with error, one, we can use standards. That allows us to identify it, and if you can really figure out what's up with your systematic error, you can mathematically correct for it. Random error, you can average. That is going to help correct for that. It's an imperfect system. And then one of the major things we're going to do is we are going to round our numbers so that, especially with random error, the number that we report is rounded such that what we report is known to be true. The random error has been rounded away. The more random error we have, the more aggressively we have to round, the less level of precision we have, obviously, because we get all that random error. The higher quality of the instrument, the less random error we have, the less we have to round, and the more actual numbers we'll get. So when we're dealing with this one way we can do and try and figure out our rounding and how to handle that random error is with significant figures or significance. This is going to be what we know that we've measured, things that we're confident on. By the way, there are other much more advanced ways of dealing with this. I'm only going to go for the fairly basic ones, which is significance. Now, here's the caveat, though. Significance means that we are confident within certain limits that this is true. We have measured in it, and it is real. It's not just random noise. In English, we use significance to mean meaningful. In science and in statistics, the significance just means it has been measured and it is almost certainly true. It doesn't necessarily mean it's meaningful. I like to give the example. If I gave you a penny, your personal wealth has significantly increased by a penny, 1 cent. Not enough to be meaningful. Most people will just walk by them. They won't even bother stooping to pick them off the ground because the things are nearly worthless. Significance is measurable. Meaningful is, does it actually affect stuff? And that's one area where you see the media. It's like, this is a significant improvement in your whatever. And in reality, it's, yes, it's measurable, but not enough for you to actually care. It's not worth your effort. So when we're looking at numbers, we usually look at which of those numbers are significant, which one of those have been truly measured, and we call those significant figures because each digit in the number is called a figure. Okay, so when we're doing our results, or when we're calculating stuff, all our numbers are only as good as the ones we started with. So we want to look at our actual raw measurements, our raw data, and figure out how much random error is in there, and then sort things through. Obviously, if the error is through the roof, then we don't want to be dealing with that. But we want to be able to report a number that is the same rounded to what the true value is rounded. That way we can get rid of our error. Okay, so when we are doing this, we want to keep track of which numbers we have confidence to. And that usually is based off of our instrument. Obviously, we can do more advanced ones with standards, but we're going to just rely on our instruments. Any number that our instrument actually measured is going to be significant. With a digital instrument, it basically just shows up. Here's your number. Just write it down. They're all significant. Any extra numbers on the side, they're not significant. With analog instruments, it's a little bit different. It's a little bit kind of odd. Analog instruments are going to have tick marks. Tick marks are going to be labeled or not. Depends on the nature of the instrument. But each one has a value, and usually those tick marks, they're close together, but your eye can estimate between the two and can do a pretty good job. So usually we say the significant figures is one more figure past whatever the tick marks are. And I know in some circles estimation has got this bad rap. It's not. It's an important skill, and your eye is actually pretty good. Estimation, yeah, it's not completely perfect, but it's there. It definitely has value. It has been measured. You are measuring it. You're just doing so with your eyes, which aren't as bad as some folks might lead you to believe. Just because it's not some fancy computer, just because it's your boring basic eyes, doesn't mean it's bad. So you can estimate, which is not a dirty word, between the two tick marks, and you get one more significant figure. And sometimes that significant figure can be really important because the story of what's going on can easily be that last significant figure. I had a friend of mine who worked for a chicken company. At the time, it was the second largest chicken company in the world. So we're talking a lot of chickens. And his job was quality control on chicken feed, because when you got that many chickens, you don't take anything for granted. And he would check train car loads of chicken food to see if it was met all the quality certificates. The chicken nutritionist, because you have a chicken nutritionist when you have that many chickens, walks up to him one day and goes, "Hey, Joe, while you're checking the chicken feed, if it's supposed to be 40% protein in the soybean meal that we've got, but give me a call if it happens to be 40.1% protein." Now, it's not much different. But here's where, things get interesting. With that much chicken feed, you can blend the chicken feed a little bit different. And the chicken nutrition's like, yeah, I can reblend it. We have to add protein to it. But if it has a little bit more protein, I can add a little bit less of more expensive protein to the chicken feed. And I'll save the company $100,000 that day. If you're able to save the company $100,000, you can justify your job real quick. You imagine you don't get paid. You might get paid $100,000. With benefits, you might do that a couple of times. But that means, if you've got a really good paying job, you only have to save the company $100,000 a couple of times a year to justify your existence. And the economy is sometimes better than it is than other times. So keep those significant figures. They might be worth more than you are, if you know what I mean. Now, when we're looking at numbers and you're actually writing them down, not all numbers you write are significant because they could also be there due to math issues, because what we use is the 0 for a placeholder. So when we're looking at a number that's been written down, because obviously we have to figure out what digits are significant in order to handle the calculations, which we'll get here in a slide or two. Zeros are the odd ones. Not 0 obviously was measured. Otherwise, why would it be a 7 or a 3 or a 2 or a whatnot? But zeros, they could have been measured, and it just happened to be right on a tick mark or something or other. Alternatively, the 0 could be there as a placeholder because you've changed the scale. You've moved your decimal point back and forth. In which case, it's not that there's an issue with that number, it's just that you don't get to add precision simply by moving a decimal point. So those are what we consider not significant, and once we do the calculations, we can't rely on those. It's not that they're wrong, they are 0, it's just that they didn't add any precision to us. Generally speaking, if you've got a number that's less than 1, which quite often you do, wherever you've got a non-zero number, and actually this is always the case, if you've got a non-zero number, it's significant, and you can count these up, and that's an important skill. A 0 between two non-zero numbers, that's going to be significant. Any zeros at the right-hand side of your number, well, those are kind of odd to have there, so they're almost certainly significant. So those guys, we call them trailing zeros. Those are significant. It's the zeros on the left-hand side of your number that are generally not going to be significant. Those are placeholder values. It's not really that you measured them. It's just that if they weren't there, your number would be a factor of 10 larger. Also, it's very common in the sciences to put a 0 just to the left of the decimal point in the ones position when you have a value that is less than 1. That's what's considered a safety 0. The idea is that if I'm writing that number out and I put a decimal point there, especially if it's going to be like 0.2 or something, it's possible someone could miss the decimal point. So you can imagine, you're giving, the order is to give a patient, say, a quarter of a milliliter, so that'd be 0.25 milliliters of some kind of drug. But you can imagine someone wrote it out badly, and the decimal point wasn't made very well, so it looked like 25 milliliters, and now all of a sudden you're off by a factor of 100, which is probably going to kill someone. So what you do is you put a 0 in front of it. So that way it's 0.25, so that if you look at it, it looks like 0.25. What idiot puts a 0? Oh, 0.25. Yeah, that makes sense. And once again, we do this in the sciences. The classic story of Popeye. Popeye ate spinach because a paper had come out saying that spinach had all kinds of iron, as much as some meats had, where vegetables had other vegetables had other values. Well, actually, spinach is right in line with all the other vegetables for iron content. They just got the decimal point in the wrong spot. But, decimal point in the wrong spot, we wouldn't have had Popeye. So, trade-offs. We later sorted that typo out. So that's to avoid typos. Once again, it's there to avoid typos. It's not there because it was measured, therefore it's not significant. And once again, you're going to want to count these up because once we start doing calculations, we're going to have to rely on counting up these significant figures to figure out where we have to round our final answer to. Okay, large numbers, ones that are much larger than 1, there's a rather odd scenario. So those zeros are both to the right of the number, and they're placeholders, so that they could have been measured, or it could simply be there because of moving the decimal point around and converting and whatnot. So there's two schools of thought. One says, don't write numbers like this, just use scientific notation. Other school of thought says, if there's a decimal point, then it's significant. If there's not a decimal point, then they're placeholder values. I usually go with the decimal point, no decimal point school of thought, but it's always safest to write in scientific notation. By the way, speaking of scientific notation, when you're writing it there, scientific notation, it's going to be broken into three parts. The coefficient, which is the number. Remember, the coefficients can be between 1 and not quite 10, so 9.9 repeating. It's between those two. Now, there is an engineering notation where that will expand out a bit more, but in scientific notation, it's going to be there. Then you have times 10 to the whatever. The times 10 is the base that's telling you basically what counting system you're using. Are you using base 10, base 2, so binary, base 16, which would be hexadecimal, whatever. So you're going to have base 10. This is telling you it's base 10, which it's going to be base 10. I mean, apart from computer programmers, just about no one uses not base 10. And then you've got a exponent that tells you, what order of magnitude your number is. That's how many times 10 you have. For significance, every single digit, no matter what it is in the coefficient, is significant. The rest of the number is not, because the rest of the number is the placeholder. And that's telling you scale. That's not telling you precision. The coefficient is telling you precision. Okay, we're going to get into calculations here in a little bit, but this rounds up looking at numbers. You do need to be able to figure out what numbers are significant and which ones are not, and that's going to become clear in the calculations part. So, hope you had fun.